Okay, so the adventure continues. Up to this point, we've been spending a lot of time looking at OpenGL. We've been creating various types of applications that allow us to manipulate graphics in our own virtual worlds. But one of the things we haven't really addressed is a way to give the programmer complete control over the pixels that get rendered out to the screen.
Right.
I mean, think about it. The way we've looked at coloring our polygons so far involved what? Let's see. Using the built-in OpenGL Phong lighting model. We had the ability to, of course, give lighting data to the vertices. We could give color data to vertices.
And we had texturing.
And we could bring textures in. And then, of course, just through little tricks with blending between. And
right.
that's really it
Yep.
for our control of color in the end. What we saw in regards to a final rendered image. Now, with shaders, we can go so much further. So starting now, over the next, 8, 9, 10 videos, we're going to take a little bit of a break from OpenGL. Don't worry, we're going to go back into our little SDL demo, and we're going to continue adding OpenGL stuff.
Right.
Okay. But our primary focus is going to shift over to the world of shader development. So the first thing we need to do is talk about shaders and find out what they are.
Right.
Joel, what's a shader?
Well, basically a shader is something that allows us to directly modify vertices or pixels through code. So this introduces a completely new language. Up till now, we've been using C++ for all our OpenGL development,
That's
and
right.
you could use other languages like Visual Basic or whatever. With shader development, we can write a complete shader that modifies the way pixels work. We can write our own lighting models with Blinn or Phong, our own per pixel lighting model.
Right.
But this requires us to have a complete new language that defines how pixels interact with the normals, the lights, etc.
So we can kind of mix the two worlds together now.
We do.
Now, this is interesting. A second ago I said, because you mentioned vertex manipulation.
Right.
So with a shader, we can manipulate vertices. We can add additional information that a fragment shader, which is something we'll talk about in a minute, that can use, or we can simply move the pixels around if need be. So we can affect color. Vertices, yeah, that's what I meant. So we could actually have a piece of geometry that's deforming, and that deformation has been caused from a shader.
Exactly.
That's very interesting. Now, this is something that's going to be plugged into the rendering pipeline.
Yep.
So we're going to go back and visit the rendering pipeline that we talked about way back, 17, 18, 19 hours ago. And we're going to show you guys exactly how it plugs in. But the bottom line is this. We have the ability to manipulate vertices, and we have the ability to manipulate the final pixels that get rendered out on our screen, and we can control them just about any way you can imagine.
That's right.
And the idea, of course, is to do this all in real time.
Yep.
So to give you an even better idea of shaders, let's talk a little bit about shaders history.
Right, or how did it all start?
That's right.
Basically, it all started around 1988 when Pixar decided to have RenderMan, and they sent it out to the world first time. And RenderMan, what was really cool about this rendering engine, not real time, but it gave programmers, artists, the ability to directly modify what was finally written out to their image.
Exactly.
And with that kind of control, everyone was like, wow, this is amazing. They had complete control over what lighting model they used, how pixels were deformed. They could write displacement shaders. So they had just an unbelievable amount of control.
The bottom line is this. We were no longer worried about just our regular lights that we threw in the scene and textures.
Yeah.
We were now set with the ability to pretty much give any kind of image that we want.
Right. With just a few instructions, simple code, you could determine the entire...
You can do things that you simply cannot do with textures.
That's right.
And a generic color and some lights.
Exactly.
That's the bottom line. And of course, with that comes the idea of getting something like that into the world of real time.
Right, and it all started out, we had OpenGL. We're discussing OpenGL. Of course, there's DirectX as well.
Exactly.
But OpenGL, the specification was released. This is just a sheet of information that people decided, okay, this is what we want OpenGL to be able to do.
And we agree upon it.
Yes, we agreed upon it. So that's what happened in 1992. In 1993, implementations began being released, actual video cards that had OpenGL specifications,
and
following
at this time,
specifications.
Here comes some real-time Polygon manipulation.
Right, and that was very, very awesome, but at the same time, it was very, very limited to what you could do. At this point, this is pretty much what we were able to do in the lessons that we've been showing up till now.
Yeah, come on, you got to think back.
Yeah,
what was some of those old graphic cards like the Trident, or what was it, the STL Velocity or something like that?
STB Velocity.
STB Velocity, yeah. See, it's been so many years. That was back around 1994, 95. And remember the pictures on the box? It was like real-time 3D, and it showed the cube and the different shapes with the textures on them. It's like, wow, that's so cool. Now, of course, we look at them and go, wow, that's really lame.
Yeah.
Because where's the bump mapping? Where's the this? Where's the that? You know, all this cool stuff that's missing. And so 2001 comes around.
Right.
Lots of development, lots of thought, and lots of people going in different directions.
Yep.
And in 2001, we started to see video cards that began supporting pixel and vertex shaders with DirectX 8.
Yep.
And the world began to change.
Right. And at that point, it was awesome. Everyone was very happy about it, but there was only a small number of things you could do. You're limited to the amount of instructions that you could have, and it wasn't in a high-level language. Back in Pixar's RenderMan, what was really cool about it was the shaders.
It was a very C-like language.
Very C-like language, very understandable to the programmers and even artists. It wasn't too hard to learn.
But now we're talking assembly.
Assembly language, the cryptic-looking commands, and you're limited to the number of commands you could even have. And that just made it difficult.
You mean I couldn't say I'm working on a particular effect and I need to loop through all of the pixels?
Yep.
I couldn't do anything like that?
You couldn't do loops.
Wow.
Just very, very limited architecture. And of course,
good
this was
job
the problem.
Security for those that wrote shaders back then.
Yeah, no kidding. But that didn't last long.
But that didn't last long at all.
By 2003, and this was for DirectX, there are ways that OpenGL could also utilize pixel and vertex shaders, but it was through other means. And it was at that point that OpenGL decided, okay, we need to have our own shading language.
Of course.
And so OpenGL shading language, now termed GLSL, was invented and approved by the ARB. So it was, okay, now we have our own shading language, which is a very C-like interface.
Exactly.
And it was only until 2004, which is very recently.
Very recently. As a matter of fact, the next handful of videos is really covering cutting-edge technology.
Because it's very, very new. And now video cards are starting to be released with it. So we're starting to see GLSL on our video cards in real time.
Right, which is awesome.
Very, very awesome.
Okay, so now let's go and talk for a minute about shading languages, because there's more than one language out there available for writing your own shaders.
Right. In the very beginning, as I said, we had our assembly language.
Right.
And that wasn't a language.
We didn't even put that up there. That's just directly talking to the computer.
Exactly. And now we have HLSL, the high-level shading language,
which is just for DirectX.
Right, and this is by NVIDIA. And it's only for DirectX. Well, not necessarily directly for DirectX, but, well, excuse me, let me roll back just a little bit here. CG is a hybrid version of HLSL.
Calm down. Let's just stick with HLSL. We'll get to CG in a minute.
Okay.
Jump in the gun.
So
HLSL was a DirectX shading language, a language for use with DirectX.
Exactly.
That was its intentions. And then came along GLSL a little bit later on, the OpenGL shading language. And this was specifically for OpenGL. And we're going to be using GLSL over the next handful of videos. So that's the language we're going to be looking at. And then came along CG.
Right.
And this was NVIDIA's CG language. And it's kind of a hybrid.
Right.
And it's something that would support both DirectX and OpenGL.
Right, because one thing that was really frustrating for people is that you had HLSL, you have GLSL. What if your engine, your game engine, wants to support both DirectX and OpenGL, which a lot of engines do? And you don't want to just use GLSL. You have to develop shaders for GLSL, HLSL, so you have to develop two shaders for every single thing, and that's just a lot of work. So CG was developed so that you could have the same shader work for both DirectX and OpenGL.
Exactly.
But again, in this video set, we're going to be supporting GLSL. And we're going to show how that works.
So with that very basic understanding, now let's talk about the tools required for writing shaders, for basically using these languages, if you will.
For really elite people, you always want to use a text editor.
Oh, I should smack you for that.
Yeah.
But Joel is right. A text editor would work just fine. But as we all know, we could use a text editor for writing all of our OpenGL C++ applications. We just need to go and buy or get our hands on, because there's like 5 or 6 of them out there, a compiler.
Yep.
There we go. And we're done.
Yep.
Right? But that's no good. An IDE makes life so much easier.
Right. Some sort of integrated development environment
exactly.
that allows real-time feedback on what you're doing.
Syntax highlighting, some debug information.
A simple hotkey to compile your application.
Ooh, yeah. Perhaps some sort of visual feedback, where with shaders, that could be extremely important as you go in and you start manipulating your code. You don't have to manipulate the code, then take it back over into your C++ environment, compile, run your application, and nope, that's not exactly what I was looking for. Then back over into...
And do it again.
Exactly.
It's just a lot of work.
So with the IDEs, one of the things you guys are going to find very handy quickly is the fact that we have a preview window that's going to allow us to see what the shader looks like rendered out on a model, and that's cool because we can even change models right there inside that particular shader IDE that we're using.
Right.
And we've got 3 of them that we're going to talk about. We've got ATI RenderMonkey. And it's free.
It's free.
And it's the one that we're going to introduce you guys to and use for writing our shaders.
Because it supports GLSL really nicely.
Exactly. Then we have NVIDIA's FX Composer, which is also free.
Right.
Both these can be freely downloaded from their websites. We're not going to be taking a look at this, but we wanted to point it out in case any of you guys out there were interested in this. If you're doing any DirectX work...
Right, with HLSL.
Which is possible, then take a look at FX Composer. And then now this one isn't free.
No.
Artisan's RT shader, what is that?
Ginza.
Yeah, Ginza? Maybe. Hopefully we're saying it right. It's approximately $1,000. About a year ago, it used to be...
I think it was more than that.
Significantly more, if I remember right. If you guys have not seen this, after you get finished watching the next handful of videos, and you get a kind of a really good feel for working with shaders, head over to their site and take a look at it.
Right.
They got a movie that you can download and watch. It's awesome.
Yep.
I mean, it really does give you the ability to create shaders at a very high-level, artist-like,
right, in
an
graphical
artist-like
level.
manner.
Right.
Yeah, which is cool.
I played with the first version a year or so ago, and it was really, really nice. Very easy for both artists and programmers.
Connections, node-based, the whole 9 yards. Really good stuff. Not putting down FX Composer or RenderMonkey. RenderMonkey and FX Composer are both very nice.
Very nice.
And you guys are going to see this, like I said, in just a few minutes.
And you will be seeing more of these pop up. I believe there's also a Shader Designer IDE, and that's for GLSL as well.
That's right.
So there are just a whole bunch of ones that you could use.
Precisely. All right, so the rendering pipeline. Time to go back and visit what we talked about in the very beginning of this VTM series, which was what exactly happens between OpenGL and your video card so that the polygons we want to see are displayed on our monitor.
Right.
So, Joel, remember, we got a mouse button here. We got to use it. So we're going to make this real fancy for you. Zach put a little effort in and gave us a really nice screen here. So it all begins with our vertice, our vertex data, if you will.
Right. This is what we send into the video card with our GeoVertex calls, our GeoColor, et cetera, et cetera. And then we send these vertices into the video card. And at this point, we could also do some high-order surface tessellation. In other words, if we had like a NURB surface or a Bezier surface, it would tessellate that into polygons or further smooth it out for us. And then once we have this information, it sends it over into the next phase, which is the vertex operations.
And this is where we deal with vertex lighting information, color information, any additional information we'd like to store along with it.
And not to mention, like our model view matrix, we have transformations that we have applied.
The bottom line is this. We need to massage all this into what's going to become our screen space in the end.
Exactly.
Getting it ready to be translated into pixels, if you will.
Right, and it is at this stage that we also do any clipping that's outside the screen or whatever. So once that is done, we got our data massaged and nice.
Now it's time to turn that into pixels.
Right. We need to take this 3D data that we have and transform it into something that we can see on a 2D monitor. So we have the triangle setup and rasterization. So we take our triangles and blend between them and get everything looking good. And then our fixed pipeline transform and lighting. This is where we take the pixels, the vertices,
The vertices that have the color information, the lighting information, and then we take the polygon that is formed by the pixel connections or edge connections, if you will, and then we blend our colors onto the polygons that we have based off all that data.
Exactly, and if we have texture information,
and then we apply it as well. So basically now we've got colors on our polygons that are blended properly.
Right.
The proper colors, if you will.
And then finally, you can throw on fog, you can do any stencil buffer tests, as we talked about before, depth tests, etc. And then finally, alpha blending.
And then to the display it goes.
Right.
So the question is, where exactly does shaders come into play in this rendering pipeline? And it's awesome. It comes into play in two places. The first place, if we go ahead and hit the mouse button there, dun-dun-dun-dun, is back here in Vertex Operations. you'll notice our pipeline now splits. We can go in two different directions. We can go what is known as the legacy path, which is back through the regular fixed pipeline for transform and lighting.
What you've seen up till now.
Exactly. Or we can now go the vertex shader route. We have the ability to write, when we write a shader,
right.
basically we can write two programs for a shader. You can write a vertex shader and what is known as a fragment shader or the pixel shader.
Exactly.
Both are not required.
Right.
I mean, you can write one or the other, or you can write both with the fragment shader being dependent on the vertex shader.
Right. You can pass information from vertex to the pixel shader.
That's right. Now, remember, we're dealing with vertex operations, so think about it. The vertex shader right here, this is where we can now manipulate vertices.
Right, because remember, this is where the transformations happen as well.
Precisely.
Where we use our model view matrix and multiply by the current vertex to get the new location. So since we're handling that entire process, we can determine exactly where the final vertex is going to get moved to.
Exactly. And so then we pass all that information back down the pipeline, all the way down until we get into the pixel operations, where our next shader area comes in. This is where we have the pixel shader, or what is commonly referred to as the fragment shader.
Right.
Exactly. And this is where we're controlling the color of that particular pixel.
Right, and any lighting information. And this is where the lighting model comes into play, whereas previously all we had was per vertex lighting. We can come in here, since we have the lighting information, the normal information, every information we need to write our own lighting model. Like
That's right.
Blinn, Phong, Lambert, whatever we want can be written at this point.
And check this out, guys. We're actually going to write a Phong shader.
Yes, we are.
We're going to write a Lambert shader. And we're going to do some other cool things as well.
And walk you through every single step so you know exactly
But we're going to
what's
show
going
you
on.
how to take that crazy math that you see on the internet or in the books, if you
or
know,
in the previous lighting
or
lesson
in the previous lighting lesson, and we're going to apply it for real, ground up, so that you can see how this all works. There's an interesting thing before we wrap this up, Joel. Let's talk about lighting for a second. Now, up to now, we saw OpenGL supports what? With most video cards, like 8 lights.
Right.
Now, that light, what happens when I write a shader and apply that shader, let's say to our box, and I've got 3 or 4 lights that I've set up in my scene? How are those lights going to interact with this box now that it has this new shader on it?
Well, now that we're handling every single thing about the pixels, the lighting information, everything. Those lights aren't going to do anything for us.
No effect.
We have to take into account all of that by ourselves. So we're going to have to create our own attributes and start handling lights in a completely different manner.
We're going to handle, at least through the next handful of videos, we're going to be handling the light within the pixel shader itself.
Exactly.
Controlling its position and things like that.
Exactly, the diffuse properties of the light, the color
Ambient,
of the light,
etc.
the brightness of the light,
Exactly.
Everything. And whether it's a spotlight, a point light, all of that has now been put in charge for us. We have to do it manually.
Right, and that's a really important thing to get across, because that really does help push an image to our beginners out there. You are now standing on the edge of an abyss.
Yes.
This gets into a very complicated world.
We're stepping from beginner, intermediate to advanced.
Yes, we are. Now, we're going to obviously try to keep this as simple as possible.
Right.
And the code we're going to show you is, for the most part, pretty simple.
Right. Relatively straightforward. And one thing you should understand is that, it is very simple. Some of pixel shaders, at least when you see the first examples, you'll go, wow, this is really easy.
Right.
But the moment you try to do something more complex, the difficulty just increases exponentially.
Absolutely.
It just is hard to do.
Now,
but fun.
That doesn't mean that you cannot write an application that a user can use and put lights into a scene, and those lights couldn't be accounted for by a shader.
And light the scene dynamically.
It's just a bit more complex now.
Right, it's a different frame of mind.
That's in the way you have to handle writing your shader so that it's going to use this external data in the way that the two interact together.
Right.
But it's completely doable. That's the thing that you guys need to understand. It's a really big deal. It also seems like there's one more thing I wanted to say. It's kind of slipping me at the moment.
The shader language?
No. I think that's pretty much everything we need to talk about in regards to an introduction to shader. Just remember, by the time we get done with the next, I think it's around 9 videos we're going to do, by the time we get done, you guys are going to have a really solid foundation that you can then use to go out and continue your research if shaders happens to be something that you really enjoy. Yeah.
And nowadays, I mean, you almost have to.
Yeah.
I mean, because the standard for graphics has gone up so much that this is something you're going to have to do.
Precisely. So with that, I guess it's time for us to get busy taking a look at RenderMonkey.
Oh, yeah.
So that's going to wrap up our introduction to shaders, and let's move on and see about grabbing an IDE and start doing some shader programming.